Hello everyone, I am Roxana and it is my pleasure to talk to you today about our latest work regarding recent advances in multi-objective, multi-agent decision making. Multi-objective, multi-agent systems are ubiquitous in our society, and that is why they represent a suitable framework for modeling numerous decision-making problems in the real world. In the context of this research, we are interested in the setting of multiple autonomous agents interacting in the same environment. Each individual decision maker might have a different feedback signal that it needs to optimize. In a learning setting, this is usually formalized as maximizing the expected cumulative reward. If we are in an infinite horizon setting, this becomes maximizing the expected discounted sum of rewards. So each agent is trying to find a policy pi that achieves this goal. The second part of the setting we considered in this work is multi-objective decision making. This implies that each agent takes into consideration multiple objectives while trying to solve the task. Having multiple objectives formally translates into receiving a vectorial reward function by each agent, one number for quantifying the performance in each objective. We take here a utility-based perspective, assuming that there exists a possibly unknown utility function for each agent that maps the value vector to a scalar value. This utility function does not need to be made explicit, but can be embedded in the thought process of human decision makers. In single-agent multi-objective scenarios, we can split the process of solving a problem in three phases: learning or planning, solution selection, and finally execution phase. Depending on the knowledge with respect to the utility function, we can further distinguish between three cases. If the utility function is known, we can potentially reduce the problem to a single objective by scalarizing the reward function, and then apply our algorithm and derive one solution for the execution phase. Most of the time, however, we are required to apply a multi-objective algorithm that returns an entire solution set. We can then apply the utility function when available, or allow the user to select a preferred solution for the execution phase. When applying the utility function, we have two options. If we are interested in the value over multiple applications of a policy, we will use the scalarized expected return, or SER criterion. This is the case, for example, for a hospital trying to optimize a treatment plan and reduce the mortality rate for a certain disease over all the incoming patients. If we are interested in a single application of the policy, we will apply the expected scalarized returns criterion, or ESR. For example, if we are a patient suffering from a certain disease, we are interested in choosing a treatment plan that will maximize the probability of a positive outcome for our particular situation. These criteria were rarely explicitly mentioned in the literature. SER is the default case for planning or reinforcement learning, while ESR is used in game theory. There has been a rising interest in multi-objective, multi-agent settings in different related fields. However, perhaps due to the various domains touching on this topic, the assumptions and settings vary greatly from paper to paper, making it hard to get an overview of all the different approaches. For this reason, our first contribution is to develop a new taxonomy to offer a more structured view of the field. We propose a taxonomy based on the rewards as well as the utility functions. We distinguish between two types of reward functions: a team reward, in which each agent receives the same value or return vector for executing the policy, and individual rewards, in which each agent receives a different value or return vector. Furthermore, we make a distinction in three types of utility, more or less orthogonal to the types of rewards. Team utility, which is what happens when all the agents serve the same interest. For example, when they all work for a single company or are on the same team. social choice utility when we are interested in optimizing the overall social welfare across all agents, and finally, individual utility when each agent serves a different agenda and just tries to optimize for that. I also note that the utility functions may be applied according to the ESR or SER criteria discussed before. In the same work, we also introduce and discuss solution concepts featured both in multi-agent systems and multi-objective optimization research and map them to the settings defined by our taxonomy. A few elements we look at are coverage sets, mechanism design, and equilibria and stability concepts. A coverage set contains at least one optimal policy for each possible utility function. In a team reward but individual utility setting, coverage sets could be used if all agents agree, example through negotiation, that they will always execute a policy that is potentially optimal. In an individual reward and utility setting, a coverage set can also be a set of possible best responses to the behaviors of the other agents. In game theory, the field of mechanism design takes the systems perspective for multi-agent decision-making problems. The aim is to design a system of additional payments that would, 1. Force the agent to be truthful about their individual utilities, and 2. Lead to solutions that are approximately optimal under a social welfare function. In the individual utility scenario, the utility derived by each agent from the received reward is different. This constitutes the most difficult scenario in our taxonomy. We consider that game-theoretic equilibria, like for example Nash or correlated equilibria, are suitable solution concepts as we are dealing with decision-making between self-interested agents. This analysis immediately raises the question of how equilibria are affected by the choice of optimization criteria, ESR versus SER, which motivates our next contribution. The framework we use to model this particular problem setting is the multi-objective normal form game, thus a stateless domain. These models are not new, they have been around since the 50s. The formal definition consists of 3 elements: the set of players, the set of actions, one for each player, and the vectorial payoffs, again, one for each player. This last component is what differentiates multi-objective normal form games from their single-objective counterparts. Our study has shown that the choice of optimization criteria is important, as it leads to different solutions in the case of nonlinear utility functions in multi-objective normal form games. Furthermore, under SER, correlated or Nash equilibria need not even exist. We thus encourage policymakers to also take into consideration what criterion applies for their setting when solving a multi-objective optimization problem. We have also studied opponent modeling based on action frequencies policy reconstruction in multi-objective normal form games. Our agents have nonlinear utility functions, and we're using the scalarized expected returns optimization criterion. We have introduced a novel formulation of vector critic for opponent modeling in our setting and showed that opponent modeling can significantly alter the learning dynamics. When Nash equilibria are present, opponent modeling can be beneficial for agents. In the absence of Nash equilibria, opponent modeling can have adverse effects on the performance of the players. We are interested in further pursuing the idea of modeling other agents in the system in order to allow for more informed decisions or to support outcomes with higher benefit, either at an individual or system level. Our plan is to extend opponent modeling approaches in multi-objective, multi-agent settings and contribute methods that can prove favorable even in situations in which equilibria do not exist. In the next stage, we are also interested in looking at extending multi-objective reinforcement learning methods to multi-agent sequential settings. Thank you very much for listening, and please feel free to contact us if you have any questions or ideas to discuss related to this topic.